Yeah, go ahead.
Excellent, excellent. Well, good afternoon or good morning, wherever you are. Welcome to the first session of today on privacy and applications. I'm very happy to be chairing this session and introducing you to four very interesting talks. Each talk will last 5 minutes, and we'll have time at the end for questions to all the speakers. So if you have questions, hold on to them, or if you want to type them in the chat, then we can pick them up after the last talk. So without further ado, I introduce the speaker for the first paper on evaluating anonymity of onion routing. And I don't know, I saw both Martijn and Øyvind on the chat. I don't know who's giving the talk.
I'll give the talk, Alessandro.
Sorry, and I didn't see you, Alessandro. Okay. Sorry, I saw Alessandro. Okay, go ahead.
I will share. Yeah, so I guess you're seeing the slides.
Yes, we can.
Okay. Okay, so hi everyone. I'm Alessandro Melloni, and I'll present the talk on evaluating anonymity of onion routing. Yeah, as Elizabeth said, done in collaboration with Martijn Stam and Øyvind Itreus at Simula UAB. Tor is the software implementation of the onion routing protocol, and it's a low latency anonymous communication network, allowing users to connect to destinations without revealing their identity. And since it was presented, there is a lot of research on to try to determine the level of privacy and anonymity that the protocol offers, even in case some of the nodes are corrupted. So for example, if both the entry and the exit node are corrupted, then the Tor designers state that the protocol doesn't offer any privacy at all. But research on attack show that breaking the anonymity is actually not trivial. And moreover, we have security proof showing that the onion routing protocol is provably secure. So there is a gap between the formal approaches and the real world results. And we provide an evaluation framework for the de-anonymization attacks and defenses on low latency SCN. Our framework is based on an attack, the interaction between the attacker and the network, and we use several random variables to capture the different aspects of the game. So S represents the secret, that is which users are connected to which destinations, and it determines G through protocol specifications. G is the random variable capturing the state of the game, and it contains all the relevant information. And it also determines V, that is the view that the adversary has of the game. And the information contained in V is a subset of the information in G. Z contains all the other auxiliary information, for example, training information for machine learning algorithm for the adversary. And the goal of the adversary is captured by the query Q. The information contained in V is then processed according to Q and Z to obtain an output random variable O. The evaluator then can compute an anonymity metric depending on Q, taking as input S and O. For example, we can instantiate the deep core attack by Nasr et al. In our framework. And S is here represented as a bipartite graph of users connecting to destinations. And G, on the other end, contains all the information of the network, traffic, the information of the traffic as well. So V captures the view that the adversary has of the game. And in this case is the traffic, ingress traffic between the user and the guard node, and between the exit node and the destination, that is the ingress traffic. And then the adversary will try to match ingress traffic traces with the corresponding egress traffic traces. There are a lot of different formal privacy notions, but they are usually based on indistinguishability for message-based scenarios. So they have a limited applicability to onion routing. because indistinguishability is too ambitious as a goal to be achieved by the protocol on the real world. And the onion routing protocol is circuit-based, not message-based, due to the low latency requirement. And the information that the adversary obtains in the security game is quite different compared to what they actually use and exploit in the real-world application. So our interpretation of privacy notions is based on unobservability and unlinkability, expressed in terms of the bipartite graph representing the secret S, where, for example, the second in the table, that is user destination unlinkability, represents the main goal of the onion routing protocol. And moreover, we also identified the two different types of anonymity metrics, input and output dependent. Input dependent metrics rely on concept from information theory, such as entropy and mutual information, and they are used to evaluate defenses because they capture the information contained in the random variable of the game, while accuracy, precision, and recall, for example, are, yes, indeed, examples of output-dependent metrics, and they are used to capture the success probability that the adversary experience when they try to carry out the attack. They can depend on estimated parameters, but they need to reflect such influence on their value, and they need to be adapted to the type of goal. When it comes to apply our framework, then it is of fundamental importance to give a proper definition of the random variables, meaning specifying their support and the probability distribution, so we can use that information instead of relying on sample statistics. And that allow us to have a better evaluation of the attacks or the defenses that are proposed to improve the anonymity of the onion routing protocol. So to conclude, we introduced this new framework, and we require explicit assumption of the environment, definition of the adversarial goals and the threat model, and the choice of relevant metrics. So, and that allow us to have meaningful comparison of different results, including their limitations that are not always clearly stated. Thanks for the attention. That was it.
Thank you very much, Alessandro. We'll leave questions for afterwards, if that's okay. We'll move on to the second talk of the session, Revisiting Driver Anonymity in ORIDE, a paper by Deepak Kumaraswamy, Siyam Murthy, and Srinivas Vivek. And I'll leave the floor to the speaker.
Thank you for the introduction. Am I audible?
Yes, you are. We don't see a screen yet.
Yeah, sharing. Yeah, is it visible now?
Yes, it is. Thanks.
Yeah. So, hello everyone. This talk. So this is a joint work with Shyam Murthy and Srinivas Vivek. So ORIDE is a privacy preserving ride-hailing service, but before we go into that, let's talk about some of the privacy issues that exist in current ride-hailing service apps. So the application generally has three entities: the service provider, who is actually the main provider of these ride-hailing services, and riders and drivers. The SP is modeled as an honest but curious adversary who is passive to all the information, but with the goal of maintaining a good reputation, the SP does not conduct malicious activities. Currently, ride-hailing services such as Uber and Lyft collect vast amount of information about riders and drivers, and these information also include the pickup and drop locations. And there have been several news reports lately which show these ride-hailing services misusing this information. With this goal, ORIDE was proposed by Pham et al. In the Usenix Security Symposium in 2017. ORIDE is a privacy-preserving solution to RHS. The main idea behind ORIDE is to hide the locations of riders and drivers from the service provider using encryption schemes. And these identities of riders and drivers are also hidden using anonymous tokens. The main goal that they want to achieve through this work is maintaining the privacy of riders and drivers with respect to the SP. In addition to this, they also achieve goals such as ease of use, accessibility, and ease of payment, which we'll subsequently visit. And through this, and by achieving this goal, the SB cannot perform large-scale privacy-sensitive inferences on riders and drivers. For example, identifying the general pickup location and drop-off location, or the density of riders and drivers in the zone. These kind of passive attacks are prevented here. All locations are encrypted using a public key encryption scheme. So this is one of the first privacy-preserving works to introduce encryption to the domain of ride-hailing services. Euclidean distance is used as a metric to choose the closest driver. And since the service provider does not have the actual locations, but instead has the encrypted locations, we need a homomorphic encryption scheme to compute the Euclidean distances over these encrypted locations. Now I'll describe the ORIDE protocol briefly. So in the first step, the rider publishes her public key to all entities in a zone. A zone is basically an area surrounding the rider. These zones are public. And all the riders and rider and all the drivers in the zone encrypt their locations using this public key. These encrypted locations are sent to the SP, who then homomorphically computes the Euclidean distance between the rider and all the drivers. The SP then sends these Euclidean distances to the rider. The rider then decrypts these using her secret key and obtains the Euclidean distances in clear. The rider then chooses the closest driver with the least Euclidean distance and sends the anonymous identity of the driver to SP, and then they proceed with ride matching. So the main work in our paper is a location harvesting attack on ORIDE. So in this, even an honest but curious rider with just a single ride request can determine the exact locations of about half the number of responding drivers in the zone. So this is a clear violation of the claim made in ORIDE that a malicious entity cannot obtain a snapshot of driver locations. And our attack is significant because the rider performs an honest ride request and can infer the exact locations of about half the number of drivers very efficiently. And this attack can be done only knowing the Euclidean distance between the rider and that particular driver. So what are some consequences of our attack? There could be possibility of physical assaults when the location of drivers are revealed, and there have been reports previously where information about drivers' locations have been used maliciously. Another consequence is that this allows a third party to obtain the density of drivers in particular region in the city based on where their current locations are during a ride request, and this can be misused by competitors, for example. So the main theme of our attack asks the following questions. Given the Euclidean distances, are there really infinite solutions to this equation where the Euclidean distance is computed between the rider and driver? A key observation is that since these locations are encrypted using a somewhat homomorphic encryption scheme, ORIDE uses a suitable scheme such as UTM to convert the floating point locations to integers. And by the value of n in the application scenario, we observe that a manual enumeration to obtain lattice points on the circle defined by n can give the potential driver coordinates. And our main motivation for this is the Gauss circle problem, which investigates the number of lattice solutions to the equation x squared plus y squared equals n. And as I said before, the maximum value of n in the application setting of ORIDE is such that this enumeration is computationally feasible. A further idea that can be applied is that during the time of write request, most drivers will be on road. So a further filtering can be applied to filter out lattice points that don't lie on road, and convenient techniques such as Google Maps API can be applied to this. So for example, consider the equation where xdi minus xr squared plus ydi minus y squared equals 25. So with the rider as center, she obtains a circle of radius phi around her. And according to Gauss circle problem, the average number of lattice solutions to x squared plus y squared equals n tends to pi for all n. But in our particular application scenario, we know that there exists at least one lattice solution. And while this provides a theoretical motivation, we observed that for practical values of n, we obtain around 20 lattice points on this circle. Further filtering is applied, and the points in green show that those lattice points lie on road, and the points in red do not. And the possible locations for the actual driver is now reduced to those 3 green points. Some experimental results. We run our experiment.
Up soon, sorry.
Yes, so we run experiments for varying zone sizes, and we use the NYC Uber dataset to and observe that there are around 400 drivers in the zone, and our results at the average number of driver locations after filtering turned out to be 2, and that the exact locations of around 50% of the drivers in the zone is revealed to the rider. So how do we mitigate this attack? So a driver can add a small noise to her location by choosing a suitable radius around herself and encrypting this location instead of her own. And this seems to provide sufficient anonymity in the sense that now if the rider carries out this attack, there are around 10 equally possible driver locations and not around 2. And this seems to be a practical fix to our attack. Thank you.
Thanks a lot. We'll leave questions for later. We'll go to the next talk in our session. Keita Kusagawa will tell us about the Bonnet-Katz transformation revisited.
So thank you for introduction. So can you hear me?
Yes, we can hear you and see your screen.
Okay, so let's start. So thank you for introduction. So I'm Keita Kusagawa from NTT Social Informatics Laboratories. So today, I want to talk about the Bonnet-Katz transformation revisited. Okay, so let us start much definitions. Okay. So we say public key encryption is pseudo-random if its ciphertext is looks like random. So so precisely speaking, so we cannot distinguish any efficient adversary cannot distinguish a ciphertext generated by like this one. So the adversary chooses message this way, then so adversary can obtain this real ciphertext. And in the sorry, so I forgot this plus. So CT plus is a sample from ciphertext space. So we say this public key is pseudo-random if this ciphertext, real ciphertext is this simulated ciphertext. So what is the application of this pseudo-randomness? So there are, so I want to introduce maybe 2 applications. The one is the public key steganography. So steganography means this 2 guys send ciphertext, but those ciphertext looks like ordinary conversation if PKG is pseudo-random. And the right hand side, so I labeled anonymous AKE, authenticated key exchange. So if ciphertext looks like random, then so if those transcripts are also pseudo-random. So therefore, so even if we get the transcript only, then so we can the receiver and sender's anonymity is preserved. Okay. So moreover, so we want to talk about observability sampleability. So if public key is pseudo-random, this ciphertext and simulated ciphertext is indistinguishable. In addition, so we consider an efficiently sampleable and explainable domain. So explain this explore is algorithm, and this samples randomness law. And so this randomness law is explains how we sample X. So this means that so if this X is generated by this sample algorithm with randomness law. So for example, so if this domain D is individual strengths, then so we have obvious explain algorithms. So explain algorithms take X and just output this X. And in addition, so we have explain algorithm. So for example, so this G is sorry, so order of parameter of subgroup of ZP star. And we say PK is a public key encryption is overly-based sampleable if ciphertext and its random explained randomness is indistinguishable from randomly generated randomness and ciphertext. So ciphertext is this is a real ciphertext, and this row is generated by explain. Or this row plus is at first chosen, then so ciphertext plus is generated by this randomness row plus. And if we cannot distinguish those two CT row and CT plus and row plus, then we say public key encryption is overly sampleable. And they have this OS has good applications. For example, so we can construct universally composable no-interactive bit commitment if we have a trapped commitment. And in the right-hand side, we have a simulation-based selective opening CCA secure PK scheme combined with some information theoretical secure cause and hash. And so this is the main body of this talk. So we found that the Bonney-Katz transformation, which transforms weakly secure tag-based encryption into the strongly public secure encryption, strongly secure public key encryption. And we found that this Bonney-Katz transformation preserves pseudo randomness and overall sampleability. But unfortunately, so Carney-Harvey-Katz transformation failed to preserve it. This is a summary of our talk. Thank you.
Thank you very much for your talk and for being on time. We got the last speaker of this session, presenting the paper ZK Attest, bringing group signatures for existing CDSA keys by Arnaldo Faz Hernandez, Watson Ladd, and Deepak Maram.
Good morning. I'm going to talk about ZK Attest as soon as I figure out how to turn off my background so I can hold up my prop. So what I'm holding up, and it's not very visible, is a hardware security token. And the motivation of our paper is using these tokens in an anonymous way. So when you sign into a website with one of these, you tap the little button on top, and that tells the website gets a signature with a key on here. And when you initially register, the website may ask you to prove that your hardware device is in fact genuine. And these are very common. If you have a recent Mac, you have one built into the keyboard. If you have a recent iPhone or some models of Android phones, you have one built into the phone. The problem is that this attestation showing the device is genuine consists of a certificate chain with a device key at the root, or sorry, device key at the leaf, and then chains up to the root, which is held by the manufacturer. And therefore, this chain, when presented to a website, uniquely identifies the batch your device was made in. And they're supposed to be big batches. They're not always, but they're supposed to be. So what we wanted to do is construct a proof that would let us anonymize these attestations. And we did that by introducing a proof of an ECDSA signature under a committed key. I'm going to hopefully do next is do a demonstration, and we shall see if this works over Zoom. So
yeah, we can see your screen. Okay.
Yep. So I press this verify with the cap button. I get a little pop-up saying, please identify the security key. So I press the security key. And now it pops up the make and model thing. And that's just because we haven't integrated into the browser yet. We've only done this in JavaScript. And now what it's doing is it's talking to the key, it's getting back the signature, and now my client is computing a proof. It's doing a large number of iterations of a commit and open sort of Sigma protocol, and then it sends it off to the server, and the server's verified it. And the server has checked that my key is on a list of approved keys, but it doesn't know which key it is. Therefore, the make and model information on my device is secret. And now it lets me pass through to the website behind it. For details on how all of this works, please look at our 20-minute presentation or our paper. And that ends my presentation.
Thank you very much. Thank you to all the speakers of the session. So we've got about 10 minutes to discuss and to raise questions before a second session on privacy and applications. Is there anyone who has questions for the talks we've listened to today? If you feel like, thanks, Watson. Watson has just added source code for the demo. So if I may, I'll kick off with a question for Alessandro on his talk on the framework that you presented. I've got one question. How challenging? I saw it in one of the open on the next steps of the research is look at the dynamic case. How challenging is it? Why didn't you immediately do that, which seems a little bit more realistic in a way?
Yeah, thanks for the question. The dynamic case, or like how we intend it, is to allow the random variables to depend also on a time variable t, for example, and that would allow us to model the evolution of the network. So, for example, the adversary tampering with the network, so dropping circuits or trying to insert cell or replying cells, or users coming and going, and that would make them the framework quite challenging, because it's allowing for example, the adversary to interact with the network would then make all the other random variables depend on the actions of the adversary, and that depends on the attack itself and how greedy, for example, what's the end goal of the adversary. That would imply different, or like probably imply different action from the adversary, and that would mean that the network itself evolves in different ways, and then it's not, it's probably doable. It's yeah, probably, yeah, I mean, but it's not straightforward in this. Probably requires, or for sure requires, quite a lot of work. It's definitely an interesting question. It's something that we want to do. We can say that obviously also fitting all these new results into the paper was not.
Sure, thanks. I was curious to understand. Probably in my head the dynamic case meant something else, so I'm glad you clarified that. Thanks. I see in the chat there's a question for Keita. Keita, do you want me to read it out, or are you happy to take it yourself?
Yeah, so the question is from Andreas, and Keita, is the ciphertext space allowed to depend on the public key, or does your result show that you cannot you cannot link a ciphertext to public key even if you know the message? Yes. So yes. And so should randomness and real sum probability. So should randomness can, in the definition of should randomness, we can the ciphertext space can depend on the public key. And I also define a strong should randomness as so ciphertext is independent from the public key. And so yes, and for the second question, yes, my result shows that yes, we cannot link a ciphertext to public key. So even if we know the message, yes.
Okay, Andreas, are you happy with this? Great. Any other questions? I wanted to ask. I know we're short on time, and the ORIDE presentation went a bit over, but at the end, I wanted to understand: were you able to completely fix the attack so to protect the driver's anonymity. I think you had to quickly go over it. I just want to know, is that fixed now?
Oh, yeah. Thanks for the question. Yes. Okay, Deepak, maybe you want to answer. Okay, thanks.
No, firstly, apologies for going over the time. Yeah, we were able to fix it now, in the sense that now the driver enjoys a good amount of anonymity with respect to the rider. Sorry. This means that from a rider's perspective, there are many equally possible locations for the driver. And hence the probability of finding the actual driver is very less.
Okay, great. And is Oride used? This is pure curiosity. Like, do you know if
it has not been practically deployed yet, and there have been follow-up works of Oride which use more complicated structures such as road network embeddings to accurately find the closest driver, but they are still inefficient in practice, and they are only of
we are not aware of any full-fledged deployment of this protocol.
Thank you. We have time for one last question. If anyone has any comments, or if not, we'll wrap up this session. Thank you very much to all the speakers, and I guess you'll have a little break before coming back to the second session of the day. Thank you, everybody.